Hello and welcome back. I am George Trimble, and this is Lesson 2 of Celestial Navigation. We left off last time with the understanding that it should be easy to find your position from a sextant site and time. We decided that by finding the altitude of a celestial body and finding the co-altitude, which is 90 minus that altitude, the angle so discovered at the surface of the Earth is the same at the center of the Earth, and that each minute of arc, in other words, you take the degrees of separation at the center of the Earth between two locations on the surface, multiply by 60, and you have the minutes of arc separation between them. We decided that the distance between them is simply that number of nautical miles. And while seemingly a simple answer, it's not practical because we would require a map big enough that our compass could be placed on the sun and its position on the surface of the map, and swing an arc to find our circle of position. And we decided for practical reasons that that can't be done. And so I promised I would show you a workaround, how to actually make that information practical, the altitude of a solar or celestial body, I should say, and the time of the site. And that's what we'll do today. We'll discover how St. Hilaire comes to the rescue and provides us with a handy and really, just a very cool means of getting ourselves onto the map. And I also promised that before we got started, I would show you your first lesson in celestial navigation, and that is how to find your latitude using a simple homemade device involving a protractor, a straw, a string, and a nut. And we can use this as a primitive sextant to find our latitude on Earth. So here, I've got my little, it's called a dioptra. It's a primitive sextant, if you will. And I'm going to show you how to find latitude by Polaris. And for those of us in the northern hemisphere, Polaris on a clear night is always visible above the equator. So let's look at the Earth here in profile. This is a side view. I've got the Earth's equator drawn in, and we're way off in space and trying to discover something about the geometry inherent in the light of the stars raining down on Earth, and particularly this star, the North Star, the pole star. You'll see that the light from the pole star drops straight down to the North Pole, and in our mind's eye, or although it doesn't happen, I should say, we're going to extend this ray of light right down to the center of the Earth. And I'll remind you that all of the light rays from this star hit the Earth all over the Earth where it can be seen in essentially parallel rays because the star is so far away. And so it interests us that this particular ray hits the Earth here, and it's of interest to us because that's where we are, and it's the ray we can measure. And you'll note that the zenith line is an imaginary line here going from the center of the Earth through our feet, out of our heads, out to infinity. And there is some geometry created by these lines, as you'll see here. We measure alpha, the angle from the horizon to the light ray from the star Polaris. We can subtract from this 90-degree angle created by our red horizon line and our zenith line. We can subtract alpha from 90 degrees, and we come up with this angle 90 minus alpha for the yellow and black lines and the angle they make. And notice here at the center of the Earth, again, a yellow and a black line. And because Euclid tells us that corresponding angles are equal when two parallel lines are cut by a transversal, we know that this angle at the center of the Earth must also be 90 minus alpha. And so we have only left to decide, well, what is this angle here, this piece of pi left that I'm showing here? And you recognize that the light ray from the North Star makes a 90-degree angle with the equator. And so what we have is that this leftover pi slice is 90 minus this, 90 minus alpha. And so 90 minus alpha, when the negative sign is distributed through, becomes alpha. So the original, after all this geometry, the original site we took on the North Star turns out to be our latitude. That is, in fact, this distance from here to here, and that is how latitude is defined. It is the angular separation between your position on the surface of the Earth, here. It's this angular separation between you and the equator. And so we've discovered this to simply be alpha. So you go outside with your little homemade dioptra and you sight through this straw and you see the North Star, and you have a friend either read off or take a picture of where the string hangs. For me, for example, in Ohio, my latitude is 41.5 degrees. That string will hang right through 41.5 degrees, and I have discovered my latitude. And in fact, sailors long ago would use a similar technique of keeping a star, some star. It didn't even have to be the North Star, and I can show you how, if you know the declination of the star, you can use it to discover your latitude as well. But you keep a star at a constant altitude as you sail east or west, and you'll sail down a line of latitude. Now, you have no idea where you are in terms of longitude, and we have yet to discover that in our talks, and I'll show you how. But and so you would not know when you would make a landing, say, sailing from Africa to the Caribbean. But you know you'll get there eventually, and because you're sailing down a latitude, you know approximately where you will land. So there's your first lesson in celestial navigation, latitude sailing. Now, you can do this with a sextant as well with greater accuracy, and I'll show you how with a sextant and St. Hilaire's method, we can also discover our longitude. But as I've mentioned previously, longitude is all tied up with time because the Earth is rotating. And so it's going to require somehow taking into account time. So let's talk about longitude and latitude, and let's talk about something called the Greenwich hour angle and declination. First, longitude and latitude. At some point in the past, it was decided that we would choose one meridian or line of longitude and just declare it by fiat the 0 point for our system, and that is the line of longitude which goes through Greenwich, England. And I've labeled this line of longitude as G. And all values of longitude west of Greenwich are counted as negative, and all those east are positive. And they count from 0 degrees all the way around to the back, and they meet at 180 degrees. So all of these values, 0 through negative 180, go through the west, and 0 through positive 180 go around the other way to the east, and they meet in the back. So you have to really remember that west is negative and east is positive in this system. And of course, the latitude is denoted north or south, where south by convention is negative and north is positive. So you've got north latitudes and south latitudes. And there you go. Each value in the latitude-longitude system is either negative or positive, depending on its direction. Now, in contrast, when we describe things that are not on the surface of the Earth, but things that are up in the sky, we don't talk about latitude and longitude. We have an analogous system of nomenclature, we use what are called the Greenwich hour angle and the declination. Now, the Greenwich hour angle is referenced from Greenwich in the sky, wherever that is, and it goes only to the west all the way around through 360 degrees. So when we talk about the Greenwich hour angle of the sun, for example, it is some number with a starting point of 0 that wraps to the west around through 360 degrees. And then declination is analogous to latitude. And so it is above or below the equator, north or south, and it has the same convention with regards to the sign, positive or negative. So declination is either north declination, positive numbers, or south declination, negative numbers. And Greenwich hour angle is always some number which is positive, and it is understood to go from Greenwich through the west to the east, 360 degrees. So here we have a Greenwich hour angle of the sun on the equator, in other words, 0 declination, but something like 300 degrees or so of Greenwich hour angle, say 340. Here we are right at 360. Now we go back to 0, and we have come to maybe 20 degrees of Greenwich hour angle, 80 degrees, and so forth. Okay. The next concept I want to introduce you to is something called the complement of a value. In geometry, we understand that the complement of an angle is however much more we need in order to make 90 degrees. So if you have a 40-degree angle, its complement is 90 minus 40, or 50. In other words, it's the balance of a 90-degree angle that's left once you remove your starting angle. And there's something called a supplement, which is related to how much is needed to make 180 degrees. But for now, we'll satisfy ourselves with just understanding the complement of the value. It looks like this. Here's a 90-degree angle. Here's some angle that we've cut out of that 90-degree angle. We'll call it beta. Whatever's left over is its complement, and that's this, 90 minus beta. And the truth is that had we declared this is the value that we cut out, then this would be the complement of that value. So we say the complement of beta is 90 minus beta. And we can say that the complement of 90 minus beta is beta. Okay, that's important because it'll help us define something called the navigational triangle, which I will show you here. The navigational triangle is the geometric figure that we hope to solve to find our position on Earth. And I'll show you here how that works. Now, we have the sun in the sky above its subsolar position on Earth. Okay, and I've extended that line to the center of the Earth so that the angle from the equator, shown in this line from the center of the Earth to the equator, shown in black, to the line of the sun in yellow, that's called the declination. And in this case, it's north, and so it's positive. The co-declination would be however much is left over up here between this black line and this yellow line. Whatever's left over is 90 degrees minus the declination. That's the co-declination. Okay? And here, I show... Sorry. A little too much of me than you wanted to see. Here I show the sailboat, not the sun, and I show that its declination is called the latitude, since we're referring to a terrestrial body. Its latitude is this angle, And the balance from here all the way up to the North Pole, this angle is called the colatitude, 90 minus the latitude. And although this is harder to show, I have shown it to you previously, and I'll bring forward the geometry from a previous slide. But this value, this arc between the boat and the sun on the surface of the Earth is called the coaltitude. And you might recall, and it represents the number of nautical miles that are represented by the number of arc minutes at the center of the Earth. And I'll show you that geometry here again. You'll recall that the boat measures the altitude of the sun. These are the sun's rays here. And this altitude is a measured value. We calculate the coaltitude up here by subtracting from 90. And we recognize that two parallel lines here, yellow and yellow, crossed by a black line here, a transversal, create corresponding angles that are equal. So this coaltitude at the center of the Earth is the same above our head, okay? And we decided that there's a relationship that 1 arc minute of a degree, that's 60 times the number of degrees represented here, 60 times this value, okay, is this value in arc minutes. And for each arc minute at the center of the Earth, we have a nautical mile at the surface between these locations. And that's where I get this value here on the surface of the Earth. It's the distance, the coaltitude is the distance separating the boat and the sun and their geographic positions. And so when you combine all of these three pictures, the co-declination, the colatitude, and the coaltitude, they join with their apices being the North Pole, the celestial location or the geographic position of the sun on Earth, and the boat. And they're connected by the colatitude of the boat, the co-declination of the sun, and the coaltitude between the sun and the boat. This is called the Navigational Triangle, and it's an important geometrical shape for us to make progress in position finding at sea. So let's look at the celestial triangle again and combine it with what else we know about the geometry on the surface of a sphere. Here we'll place the sun, the boat. That's the longitude of the boat from Greenwich. This is the latitude of the boat up from the equator. We've got the declination of the sun, which is kind of like the latitude. It's relative to the equator as well. And here we've got the Greenwich hour angle of the sun, the amount of angular degrees from Greenwich that the sun is positioned at on our grid system. And it's analogous to longitude. So if this is the latitude from the equator to the boat, that's the colatitude. If that's the declination up to the sun from the equator, we've got the co-declination, and we connect the positions of the boat and the sun with the coaltitude, recognizing that the coaltitude is the number of nautical miles that separate them on the surface of the Earth, if expressed in nautical miles, but that same number expressed in arc minutes is the angle at the center of the Earth that separates these two objects. All right, to beat a dead horse. Here's a little reminder of that, because it's the key point that many people forget, is this relationship. Okay. Now, I'm introducing now a new term called the local hour angle. It is the angular difference between the boat and the sun. In other words, it is the difference in longitude between them both, or we should say the difference between Greenwich hour angle and longitude. And you can see if you have this Greenwich hour angle here for the sun and we subtract the longitude, what's left over is from here to here, and that's the local hour angle, and I label that angle. And then I've got this angle here, which I call the azimuth. It's the angle between the boat at the boat, I should say, between due north, which is what this line represents up to the North Pole. From the boat's perspective, this is just its local meridian, and it runs due north. And so it is the angle between due north and the sun for the boat. Okay, we call it the azimuth. Now, the azimuth is one step away from a value that we need, which is the zenith. It's the angle, it's the angle we're going to use on the map when we position ourselves on a map. And so it's what we measure on the compass rose of the map. So if you take 360 minus the azimuth, we have the zenith. And as you see here, the zenith is defined by starting at the boat's location from north. That's this colatitude line. We're going to wrap around through the east, through the south to the west until we reach the coaltitude line. So it's from colatitude through the east to the coaltitude. So it's the supplemental angle, the supplement reaches 180. I don't know what they call this angle, but it adds to 360. So the zenith plus the azimuth come to 360 degrees. Okay, now here I show you how the situation can be different. The situation can be such that the boat is located over here and the sun is located down here. And then we would say, okay, well, the azimuth is simply the shortest distance between north and the coaltitude line, or the sun, the line from the boat to the sun, and so that's the azimuth. And I told you before that the zenith is nothing more than the clockwise rotation from colatitude through the east to the coaltitude line. And it so happens under this circumstance, the azimuth and the zenith are one and the same. Here, they have to sum to 360. Here, they're one and the same. So, looking at a top view down from the North Pole, okay, we've got two circumstances. Here we've got the boat located here at some west longitude, meaning a negative longitude from Greenwich, and we got the sun at some greater Greenwich hour angle, which is positive from Greenwich. Okay, and you can see how the difference between the Greenwich hour angle here in green for the sun and the west longitude for the boat in red, the difference between them is this local hour angle. And that's the angle between the sun and the boat. This is a top view from the north. And since by convention west longitudes are negative, algebraically it is the sum of the Greenwich hour angle plus the west longitude that gives us this local hour angle. So Greenwich hour angle plus west longitude, which is understood to be a negative value, so algebraically they sum by subtracting, gives us the local hour angle. That's the top of the triangle up at the North Pole that I showed you on the previous slide. It's the angle at the top of the triangle. Now, if their positions are switched, here's the sun and here's the boat. Now, because the boat is farther than 180 degrees away from Greenwich, and I should say farther than this point here, it's on this side, so we understand that our longitude will be understood to be to the east, and that's a positive value. So east longitude, here's the Greenwich hour angle for the sun in green, and so you see that, again, we sum them. But this time, because east longitude is a positive value by convention, a sum is a true sum. And they sum to the local hour angle again. And so the rule is the local hour angle is just the sum of the Greenwich hour angle and the longitude. And we just remember that west longitude is always negative. Now, for use later, I'll show you that if you're going to be one of those guys who uses the sight reduction tables for marine navigation, you're going to need to express this angle as some number between 0 and 360. And sometimes you'll come up with a value like 370, okay? for example. And you have to subtract 360 from 370 in order to bring that number into range, because 370 and 10 degrees have the same they have the same trigonometric functions. The cosine, for example, of 370 is exactly the same as the cosine of 10 degrees because they differ by 360 degrees. The trigonometric functions are periodic functions, and so if we're going to use the lookup tables, we need to make sure that the value is expressed in some number between 0 and 360 degrees. And likewise, if you come up with a negative number, you need to add 360 degrees to bring it into range. If you're going to use the calculator methods that I've showed you, that I'll be showing you here today, then you don't have to worry about it because the numbers are all the same. Okay. And I'll remind you, the problem that we have with just measuring the altitude of the sun, discovering its co-altitude by subtracting it from 90 degrees and realizing that that value at the center of the Earth, expressed as minutes, is the distance between the boat and the sun's geographic position on Earth. The problem with that is that we can't fit that on a map. We can't actually swing a compass arc and draw this beautiful yellow circle that we would like to draw by placing a compass point at the location on the globe of the sun with a separation in the arms, the separation being the co-altitude, and sweeping a circle out. We can't do it because we'd need a 42-foot globe in order to be big enough to express your line of position or circle of position with enough accuracy for navigational purposes. And on a flat map, I remind you that circles project due to distortion in this strange oblong egg shape, which no compass can swing. A compass swings, of course, a circle. So that's the problem with just using the co-altitude. Theoretically, it can work. Practically, it cannot. So let's reestablish our previous drawing and get our navigational triangle back. All right. So, unfortunately, I got to teach you one more term, and I'm sorry. I wish I didn't have to do this. We've been talking about the altitude measurement from the red horizon here to the ray of sun where it intersects the boat. This altitude I've called the altitude, or alpha, the Greek letter alpha, which I chose because altitude starts with A and alpha is the Greek letter A. And that's all fine and dandy in geometry and astronomy, but sailors like to call this the observed height. I'm sorry, but yet another term to learn. And so if this is the observed height, this is the co-observed height, the co-altitude. And this is also the co-altitude at the center of the Earth, as we've said before. So the co-altitude, when I say it, just means 90 minus the altitude, or 90 minus the observed height. So get used to CHO, observed height, in the parlance of navigational speak. Yeah, me too. All right, now we come to the cool stuff. I'm going to put me down here. Now, remembering our navigational triangle, understanding that the sun is located at this corner of the triangle, the boat here, and the North Pole here. We're going to discover the St. Hilaire method. It's the workaround that allows us to put our position on a map. Now notice we know in this drawing we've identified three sides of a triangle, we've identified an angle and another angle, and we're missing this angle here. All right. Now, this is a map I've drawn out, and I've put the compass rose on the map here. And I'm going to place the sun above our map, hanging in the sky, and the boat in the water down on the map. and I drop a pillar, an imaginary pillar, from the sun to its geographic position directly below it on the surface of the Earth. That geographic position for every second in time for every year of 2015 is located in this book, the Nautical Almanac. We can look it up. And so we know the geographic position of the sun. You'll recall that this line, this radius of a giant circle upon which our boat lies, that normally I display in yellow, the circle that's swept out by this arc, this radius, this line here, this radius is called the coaltitude. It connects the sun and the boat. Okay, the coaltitude. There's the circle of position that the boat must lie on in order to measure the altitude of the sun that it measured in order to get that coaltitude. Only boats located on the surface or on the circumference of this circle would measure that altitude for the sun. Boats further away out here would have a narrower altitude measurement for the sun, and boats closer inside the circle would measure a higher angular altitude for the sun. So we know that with this coaltitude, we must lie on the circumference of this circle. And there's the altitude or the observed height that we measured from that boat location. Now, what we're going to do is arbitrarily pick another spot on the map. And it doesn't matter as long as it's on our map. It really doesn't matter. Now, you might think this is arbitrary, and it is, but I'll show you that it just doesn't matter. With perfection, it will show us where we're located, even though we choose some random spot. I chose that spot, and I'm going to call it the assumed position, because let's assume for just a moment that we are there. I ask, what would we experience were we located at that spot? Well, there's a line that comes from the geographic position of the sun through our spot, our assumed position. And if it were to sweep around in a circle, it would create a circle of position that we know we must be on in order to measure this value in green, the altitude called HC. This is I call it HC because we don't know what it is because we're not there. We can't actually observe it. So we're not going to call it the observed height like we did at the boat. This value we're going to calculate as if we were located at the assumed position. We're going to calculate HC, which is the coaltitude. It's this. It's actually 90 minus the coaltitude, which is related to this angle here, this leg of the triangle. We call it HC because it's going to be a calculated value. And any boat located on the circumference of this bigger circle would measure a value of HC, and 90 minus HC would be the coaltitude, and therefore would be the distance from the geographic position here to the assumed position. Even if even if we had chosen this assumed position here, right there on the edge of the circle, it too would have a green line up to the sun that measures HC for the angle. All right, enough said. A line drawn tangent to the circle here, I want you to see a line drawn tangent to the big circle through the zenith line, this red or maroon line, is perpendicular to that maroon line by definition. It's perpendicular to the radius of the circle if it's tangent to the circle, and it kisses the circle at just one point. That's the assumed position. And I want you to see, now look carefully. Now, do you see how HC is a narrower angle than HO? We can pick any point on the circumference of the smaller line and draw a line up to the sun, as I've done here. And HO is the same here as it would be if I had it for the boat over here. but I've drawn it at the intersection of this longer zenith line to show you that the angle at the boat's position will be higher because it's closer, and the angle at the assumed position will be narrower. The altitude of the sun would be narrower because it's further away. This difference between the assumed position and the actual circle that the boat lies on is nothing more than the difference between the measured co-altitude and the calculated co-altitude. The measured co-altitude comes from our original sextant site at the boat. Okay? It's 90 minus the altitude. That's our nautical miles separation between the boat and the geographic position. The calculated co-altitude is a value that we will calculate, which represents the distance between the geographic position of the sun and the assumed position. And the difference between them two is just the difference in co-altitudes. Now all we have to do is have a way to calculate this value at the assumed position. And we can use the distance from the assumed position to the circle of the boat, both of which lie on our map. The assumed position might be a mile away, or 2 or 5 or 10, but it's not a couple thousand miles away like this distance here. And note, this isn't done to scale. I had to fit it all on this slide. But the difference between the geographic position and the boat could be 4,000 miles. But the difference between the boat and the assumed position will be something on the order of 10 miles or less, generally. You pick something close by. In fact, I'll show you later why it makes sense that you use your dead reckoning as your assumed position. Whatever the case, if you subtract the two co-altitudes, the observed one and the calculated one, what we get is 90 minus HO minus 90 minus HC. That's the difference between them. Let's distribute this negative sign into the parentheses, negative 90, positive HC. And what we get is a 90 minus a 90. That goes to 0. And we get negative HO plus HC. And if we rearrange that, we get HC minus HO. It's just the difference in their altitudes. Now, we measured the one altitude at the boat. We calculate the other altitude out here at the assumed position. When we subtract them, it tells us how far from the assumed position this circle of position is. It's as if we move this line of position to the boat. Now, I want you to see that, actually I'm going to back up previous. So I want you to see that even though the intersection, the tangent point of this line of position, by moving this line, this black line here, a certain number of nautical miles being the difference between observed altitude and calculated altitude, by moving that number of nautical miles in this direction until the first tangent line kissing the big circle now kisses the small circle, that's not actually the position of the boat, but the boat is on the circle of position here, but it's also sensibly on this line of position, because we're talking about a circle that is potentially thousands of miles in diameter. And so a circle running through a small section represented by your map will cross as a straight line. Here's a map, for example. A circle of position drawn through this map at this scale would appear to be linear. And this line, the line of position shown in black, approximates a circle of position for hundreds of miles. And so if I can find this line of position here, then at least for a small distance on either side of this position here, the intersection of the small circle with this azimuth line Z here, on either side of this intersection, the line is a good approximation of the circle. And so this method is called St. Hilaire. It doesn't require that our map be big enough to have the geographic position of the sun on it. It need only be big enough to accommodate some assumed position that we chose on our map. And from that assumed position, we move in the direction of the zenith line, which is also a calculated value. It's this down here, which we will calculate. And I'll show you how we can calculate these two values, the zenith, which is the angle on the compass rose that we'll take from the assumed position to the geographic position, and we'll calculate the co-altitude of the HC, the calculated altitude. So we've got the zenith direction, and this length allow us to find a place on the map through which a perpendicular line may be drawn to the zenith line, and we know we must be on that line, understanding that the map that we're using is only about this big here, my little circle. The map that we actually use approximates the segment of this circle with a line easily. All right, that'll become clearer shortly. The important thing is the difference in co-altitudes between the assumed position and the boat's circle of position in nautical miles is HC minus HO. It's also known as the intercept, and that's why this is also called the intercept method. The sun, as I said before, is generally very far away. It's not on our map. Our map is a tiny thing, maybe this big. Maybe it fits in this square. But the assumed position is on our map. So, from a side view, looking at the Earth out from space, side on, we've got the sun located here. We've got the boat located here. In fact, let's call this. This is not necessarily an equatorial view of the Earth. It's a view of the cut section of the circle of the Earth, such that the plane of the cut section intersects the boat, the sun, and the center of the Earth. So it's an oblique section. Whatever the case, we got the observed altitude, 90 minus the observed altitude. Here's 90 minus the observed altitude down here because of the corresponding angles principle. And we know that if we multiply this value, which is in degrees, by 60, we get minutes. And we know that a minute of arc at the center is a nautical mile at the surface. So this gives us the distance from here to here. Now we've chosen assumed position. There. The assumed position is farther away. In this case, it need not be so. The mathematics works out the same no matter what. But we choose an assumed position. Here's a ray of sun at the assumed position. If we were there, we would measure some value called HC. And this would be 90 minus HC, and this value from here to here would be 90 minus HC, and the length of the arc from the sun to the assumed position would be 60 times 90 minus HC. Now we're not there at the assumed position, but we can calculate the value 90 minus HC using spherical trigonometry, and I have yet to teach you how to discover these two values, HC and the zenith angle. But we do that by solving the spherical triangle, and I'll show you here shortly. Whatever the case, when I take some of this complexity off to the side, you see that here's the assumed position. 90 minus HC is bigger than 90 minus HO. The difference on the surface of the Earth is nothing more than the nautical mile separation between the boat and the assumed position. That 90 minus HC times 60 is the number of nautical miles on the surface of the Earth separating the assumed position and the sun. When you subtract this value in black and this value in white, the difference is this value right here between the boat and the assumed position, which is very convenient, and that's the trick of the St. Hilaire method. Here I show 90 minus HO minus 90 minus HC simplifies by distributing the negative sign into the parentheses to 90 minus HO minus 90 plus HC. 90 cancels, a positive and a negative 90, and what we're left with is HC minus HO. Now, we need only learn next how to calculate those values from the navigational triangle. Here I show that HC minus HO is some number of degrees. You multiply it by 60 to convert it into arc minutes instead of degrees. And an arc minute at the center of the Earth here is a nautical mile at the surface, as we discovered in our first lecture. We have Eratosthenes to thank for that little insight. So in another view, we have an understanding that this line between the geographic position of the sun and the boat, or to the assumed position, they represent radii of circles. And so we can sweep a circle out at the boat's position or a circle out through the assumed position's location. And each of those has a radius described by 90 minus HO or HC respectively. Each needs to be multiplied by 60 to convert it into nautical miles. And so this little difference is the difference between the radii. And that number of nautical miles helps us position our boat by swinging a circle not around the sun's geographic position, but essentially swinging a circle around the assumed position's geographic position, and noting where these two locations kiss, we can draw a line to represent the circle. Now watch. Here's the assumed position. Here's the zenith to the sun. Okay. Here's the circle of position that the boat lies on. That is the intercept distance, the difference between the observed and calculated as altitudes expressed in nautical miles. It's called the intercept distance. That's HC minus HO times 60. This little line that we've drawn at this distance, perpendicular to the zenith line, Z, here, for many nautical miles, represents this. It's a stand-in or surrogate, if you will, for the circle of position which we sought in the first place. And we can't draw because the sun isn't on our map. So you see that for hundreds of miles on either side of this intersection, for hundreds of miles, a line is a pretty good approximation of a circle, or at least a part of a circle, a curve. This is the St. Hilaire method. It's what we're doing. We will find the intercept distance. We will find the angle at which we need to move from the assumed position. In this case, it's just straight over to 270 degrees, but this could be any angle. And combining them, we can draw a perpendicular at that distance from the assumed position, and we know the boat must be on that line. With two lines or circles of positions, we could get a fix. And a fix tells us our latitude and our longitude both. This is the key, an important concept in the St. Hilaire method, is that the line of position so attained is an approximation of the circle of position that we seek in the first place. Now, I need to teach you next how to solve the navigational triangle and discover the co-altitude and the zenith. These are the two datums that we need in order to utilize this technique. So it brings us to what's called the law of cosines. Get me out of the way there. So we have, in a more general sense, in geometry, we name the angles of a triangle with capital letters, and the side opposite gets the lowercase. So if this is A, then this is little a. If this is angle C, this is little c. And if this is B, this would be little b. Now, I'm just going to state I should say that in celestial navigation, we've identified that A is the co-declination, little a. Big A is the azimuth or the zenith angle. The co-latitude is B, little b, and co-HC, which is what we're looking for, is little c. But in terms of this top triangle here, let me get me out of the way. The law of cosines simply stated is this. You can use this and you can plug and chug and you can do celestial navigation all your life by just taking the cosine of A, which is the co-declination, times the cosine of B, which is the co-latitude, plus the sine of little a, co-declination again, times the sine of little b, co-latitude again, times the cosine of the enclosed angle, which happens to be the local hour angle. You can come up with the cosine of C. And if you take the anti-cosine of all of this stuff over here, you're left with C. Sorry, I bounced back. Okay. So inserting those into here, C is the co-HC. It's the value we seek to find here. So using the law of cosines, we just plug and chug. We put those numbers in, and we can rephrase. This is interesting. We can actually rephrase this complicated looking formula. Instead of all these co-declination and co-latitude, co-HC, we can rephrase these trigonometric factors by recognizing that the cosine of 90 minus an angle, or the co-angle, is the same as 90, or is the same as the sine of the angle itself. So the cosine of 90 minus alpha is the same as 90, I can't say it right, this is the same as the sine of alpha itself. And so we can rewrite everything in this second equation like this. The cosine of the co-altitude is the sine of the altitude. The cosine of the co-declination is the sine of the declination. Right on down the line, right on down the line. And I've really simplified this, and it gives me the same answer. And this comes from this here comes from the trigonometric identities, which you can look up in any trigonometric text. But it is true, this does equal that. And so what you want to note here is this last term did not change. The cosine of the local hour angle is still the cosine of the local hour angle, because this was not 90 minus the local hour angle. It's just the local hour angle. So if I were to change this, then it would have to be the sine of 90 minus the local hour angle. And I've added complexity, so I did not change that last term. Now, I'm interested not in the sine of HC, but in HC itself. So I'm going to take the arcsine, which is the anti-sine of everything located on the right side. And there is the answer. I can find that magical value, HC, the calculated altitude, which when subtracted from my observed altitude gives me the distance between the assumed position and my boat's position, or close thereabouts. I'm on that line of position. It's what separates the two lines of position. Now, similarly, I want to discover the zenith value down here. So, again, I'm going to use the same idea. The cosine of this value here, A, is equal to the cosine of B times cosine C. You see, the side is equal to the multiple of the other sides, okay, plus the sine of the other sides, okay, times the cosine of the angle opposite. That's the exact same thing we did before here. It's the same formula, if you will. It's the same strategy, the relative each of these is in the same relative place. I've just shifted to a different angle now. And I'm actually interested in this value A right here. So I'm going to rearrange the equation here in a minute. But first I'm going to recognize that A, that's this, is the codeclination. So, and I plug in all those same values from here. And then I simplify using the complement identities to this, okay? And what I'm interested in, again, is the azimuth angle here, and ultimately the zenith angle. But so I rearrange by subtracting and then dividing. So I subtract this from both sides, and then I divide this from both sides, and I end up with cosine of the azimuth by itself over here. And I need the anti-cosine of both sides in order to get just the azimuth by itself. Here it is. I've just switched them around. Okay? So this is the formula right there for discovering the azimuth. And if this is understood to be the boat, then the zenith is going to be 360 minus the azimuth. If, however, the boat was understood to be over here, as you might recall, the azimuth and the zenith are the same. We saw that 2 slides ago, or 3. And notice we need the value of HC before we can compute the azimuth. And HC was calculated first over here. You see? HC appears here. So we have to first work this equation, and then we work this equation. And what we're left with is HC and azimuth. Those are the values we need to find our place on the map. So I'm going to do our first example here. This is an example of it's in the Bahamas, just west of Andros Island. And we measure the altitude of the lower limb of the sun here, the lower limb of the sun, the altitude of the lower limb of the sun on June 19, 2015. And we find that at 15:23:42 in universal time, not local time, but universal time is the time kept at Greenwich. So it has to be converted. The sextant, the sextant height, the height we measure, the height we measure with the sextant is 64 degrees, 21.4 minutes. The index error, the known error on our sextant is positive 1.2 minutes. That value is sextant specific. Yours will be different than mine. And you'll learn how to find what your index error is in a future presentation when we learn how to take this measurement, 64 degrees, 21.4 minutes. How do we use a sextant to measure the altitude of the sun? And why did we use the lower limb of the sun, the bottom edge of the sun, as opposed to the top edge or the middle? I'll explain all that in a future lecture. But we did measure the altitude from the horizon to the lower limb of the sun on this day, at this time. We came up with this value. We need to know what the error is inherent in our instrument. And it turns out that the height of our eye at the time of the measurement above sea level, say I'm standing on the deck of a ship. I'm 6 foot tall, so the deck of my ship must have been 2 feet off the waves. My height of eye on this example was 8 feet. That makes a difference because the higher you are when you take the measurement, the farther away you can see. And so your horizon becomes farther and farther away. That has to be taken into account. That's all stuff we're going to learn in a future lecture. For now, what you need to know is this is the data we've got. Here's our GPS position, 79 degrees, 32 west, 24 degrees, 35 north. That's going to be what we compare to later. We want to see how close we got to reality. So I'm going to show you that we can take 3 positions, position 1, position 2, or our dead reckoning. We can use any of these as the assumed position. I just randomly chose these 2. The dead reckoning comes from what we should be keeping with our map to get at least an estimate of where we are, as we discussed in our first lecture. we're going to sequentially use each of these as an input into the calculation of the St. Hilaire method to find a line of position. And I'm going to show you that they all give the same line of position. No variation. Each of these, without variation at all, gives the exact same line of position. Now for now, let me just end show. I'm going to go to this Excel document, and we're going to take that first assumed position, 79 degrees, 23.5 west, and 24 degrees, 26.0 north, and I'm going to plug it into a spreadsheet that I've designed. Maybe I'll keep this like this. So, on this spreadsheet, which you can simply design yourself in Excel, the yellow values are input values, and everything else is calculated by the computer. I input the sun's lower limb as the body that we're observing. I put the date in there. Here's the universal time. Notice I separate hours, minutes, and seconds into separate boxes so they can each be used to calculate with. Here is the latitude, the dead reckoning, and really this should say assumed position latitude, but as you'll see later, I recommend you always make the assumed position your dead reckoning. But whatever the case, we're going to use 2426. That comes from over here. Assumed position 1, 2426 north. It's positive because it's in the north. And we've done the latitude, we need to look down here and find the longitude. Here it is. The assumed position longitude is going to be negative 79, negative 23.5. 79, 23.5 west. Each of these values is negative because each of them is west. And I've indicated that you need to indicate the negative sign in both boxes with these little reminders here off to the side. 79, 23.5 west. Okay. Now, we need to go here to the next category, which has to do with the actually let's go here first. Let's fill in another piece of information that we already know, and that's the sextant reading. The sextant height is 6321.4, and that comes from this slide over here. I see that I've got a little mistake in that should be a 3. I've got a little mistake in my presentation. The sextant altitude was 6321.4. That was causing me a lot of trouble earlier when I was putting this spreadsheet together. But that's what it should say, 6321.4. And here it is, 6321.4. The index error is 1.2. That's given in the problem. The dip is another value, and that comes from the height of eye. Now, we need to go to the Nautical Almanac. The very first, let's see if I can get this on the screen. The very first page is a set of tables. I can't show you too much details because I don't want to breach any copyright, but under one of these tables, you look up the altitude of your sextant reading, and it depends which date. If you're between October and March, you use one table. If you're between April and September, you use a different table. We are between April and September because we're in June. April, May, June, July, August, September. So we're going to use this column of that table, and we're going to look up the altitude of the sextant reading, which was 6321.4. I look it up here, and it falls between 6150 and 6715, and the value it tells me to use is 15.5 if I'm using the lower limb as opposed to the upper limb of the sun. So 15.5 is the value that I look up for the altitude. And that's this value here. Now, before I do that, though, I need to look up the dip. This value comes by looking up this 8 height of eye of 8, in another little table off here to the side. At 8 feet, the value to use is minus 2.8. So I put this minus 2.8 in here, and I algebraically add all this up. I'm going to convert the sextant height to the apparent height, HA. That's this number, 6319.8. Okay, so when I do all this subtraction, 63 degrees, 21.4 minutes, minus 2.8 minutes plus 1.2 minutes, I get 19.8 minutes. 63 degrees, 19.8 minutes. And actually it's this value in purple that I enter into the altitude tables, and it comes up as 15.5. It really didn't change anything. But 15.5 is the altitude correction, which is then added to this 19.8 to get 6335.3. That is our observed altitude. So you see that the sextant altitude we get has to be corrected for index error, dip, parallax, altitude, refraction. All these things are taken care of by looking up the values in the tables, and we get this corrected value, which is observed altitude. That's the altitude at the boat, as you might recall. Now, we need to change pages. We need to go to the date in the Nautical Almanac. We need to go to June 19 for the year, and we go to the page dedicated to that day. And in fact, each page is dedicated to 3 days, so we have to pay attention that we're looking at the right day. But we'll look at June 19th, and we'll look up for that day what hour, and this hour is at 1500. So looking on this table, we read down on the day, and we read down to 1500, and we find that on June, let me get to the actual page. Here we go. So on June 19th, at a universal time of 1500 hours, it says that the Greenwich hour angle of the sun on that day is 4440.3. And that value goes here, 4440.3. Now, just one column over from that, it tells me the declination of the sun on the same day, which I take right now and I fill in up here. The declination is 2325.2. Okay. Now, we need to go to another page called the Increments and Corrections page. That allows us to modify these values based on not just the hour, but the minutes and seconds of the day. And so before we do, I want to point out that at the bottom of the page here, right down here, is a little value called D, delta. It's the change in the declination as the day goes by, and it's either positive or negative. And delta, in this case, is 0 because we're in June. The sun is kind of hanging out near the solstice when the declination hardly changes at all, but the delta on the 19th is 0. It's not changing. The declination is not changing much each day. But you have to decide, is delta positive or negative, and you have to put that value here. D for my day is 0. Yours might be a delta of 2.4, and you have to look at the row of data to see is delta increasing or decreasing and assign this a positive or negative value, okay? Now you're going to use this delta in the increments and corrections table. And so we flip to the back of the Nautical Almanac to the increments and corrections, and we go to the minutes for the day. So, for example, on our day, we've already looked up the Greenwich hour angle and declination at 1500 hours. We need to find out how those values are modified at 23 minutes, 42 seconds. So we find the entry for 23 minutes, and we read down to 42 seconds. 23 minutes, read down 42 seconds. And it says that for the sun, I have 555.5. which you see here. This is the minutes and seconds. I add 55.5 here. And when I add that up, it comes up to 50 and 35.8 minutes. Okay. Now for the declination, I have to go to a little table off to the side here, and I look up the declination, and it tells me what the D correction is. And my correction of 0 means a D correction of 0. So I enter 0 here. Okay? Now, when I add all these up, I get 2325.2. When I add these up here, I get 5035.8. And you recall that the algebraic sum of the Greenwich hour angle and the longitude gives us the local hour angle. So this is a calculated value. It comes from the assumed positions longitude, 7923.5, negative in the west, right? We're going to find the difference between, or the sum, which ends up being a difference because of the negative value. But we find the sum of these two values, okay, and it comes up to be 331 degrees, 12.3 minutes. Okay, that's the local hour angle. Now, off here to the side, you see all these calculated values. This value is calculated from these values, by taking 26 minutes, dividing by 60 to convert those into parts of a minute, and then adding it to 24. So 24 hours or degrees of latitude and 26 minutes is 24.43 degrees. And I did that for each of the values that are needed so that I could actually do the calculation not by adding minutes, but by adding decimal whole degrees. So all my calculations are done on this side of the spreadsheet by converting everything to decimal, or to whole degrees in decimal form. So here we've got the latitude, the declination, we've got HO, we've got local hour angle, we've got HC. Now, we find HC using the cosine formula. And if you're curious, there it is shown here. That's what's hiding in there. It's a formula. Keeping in mind that Excel does everything in radians. So you have to express your numbers in radians before you use them with the sine function, and then later you convert everything to degrees. But if you're interested, take a picture of that. If you're trying to copy my work, go ahead and take note of how the cosine formula is found manifest in Excel. It's tricky business, but there it is. Things have to be couched in terms of radians before they have their trigonometric functions applied. Okay, so in this box is calculated HC, and I'll show you how to do it. On your calculator, you can either do this on your calculator from like a written out worksheet, similar to this Excel document, or you can let Excel do the work like I show you here. But if you use a calculator like mine, this is a TI-30XA, very convenient. It's a solar calculator. It's available as a solar calculator. This one is not. But what I'm going to do is I'm going to type in the key numbers. And you see I've located those numbers by saying memory 1, memory 2, and memory 3. So I'm going to type in 24.43, 33333, and I'm going to hit store 1. Clear. Just get rid of it. It's stored in 1. Now I'm going to hit this here. 23.42, store 2. This says memory 2. It's a reminder to put that in memory 2. And then for the local hour angle, clear your screen, 331.205, store 3, and then clear. Now, I'm going to broaden this out. The keystrokes to get this value, HC, are right here. These are the keystrokes on a calculator, right here. So I'm going to, from a 0, from a clear, I'm going to start by hitting recall 1 sine times recall 2 sine equals plus recall 1 cosine times recall 2 cosine times recall 3 cosine equals second function sine, and I get 63.7. Okay? That's the number that I let Excel calculate for me on the spreadsheet. So you can do this by writing the values down on paper, doing the additions and subtractions of your increments and corrections and so forth from the tables, and coming up with these red values, the latitude, the declination, and the local hour angle. Those are parameters to be used in this equation. This is the cosine, the law of cosines equation, and that gave me the 63.7 for HC. Now, it says memory 3, which means don't erase this. It's still on your calculator. I'm going to type store 3, and now that replaced the local hour angle in 3. Now I'll clear my screen. Now I've still got, in memory 1, I've got the latitude. In memory 2, I've got the declination. And in memory 3, I don't have local hour anymore, the local hour angle. I now have the calculated altitude. Okay? And so now I'm going to use that value here, right here. And I'm going to use it to calculate the azimuth. And that'll be this value here, 86.21. And I'll show you that by doing this set of keystrokes, recall 2 sine minus recall 1 sine times recall 3 sine equals divided by recall 1 cosine divided by recall 3 cosine equals second function cosine. 86.2 is what I get. By following those keystrokes, basically we are entering the proper sequence of actions in order to perform the law of cosines on those variables, and discovering an angle of the celestial or navigational triangle. And here it is, 86.2. And I discover the zenith by recognizing that if the boat is in the lower right-hand corner, then the zenith is 360 minus the azimuth, and if it's in the upper or in the left-hand corner, lower left-hand corner of the triangle, then the azimuth equals the zenith. Turns out this is the case here for this setup. So you can program all of this into Excel, and here's the I'll show you. If F28 is less than 180, then 360 minus F34, otherwise F34. That's just saying exactly what I said previously. So, there you go. You don't need to know what you're doing. You don't need to know why the cosine formula works. You don't need to know where it came from. You don't need to know how it differs from a flat trigonometry cosine equation. It turns out that the law of cosines on a sphere looks different than the law of cosines on a flat surface or Euclidean geometry. But now you've got these two numbers. What do you do with them? You've got HC, 63.7, and you've got the zenith. What you're going to do with HC is you're going to subtract from it HO, which is up here, 63.5, and you come up with 7.12 nautical miles. And it is away from the assumed position if positive to the assumed position if negative. In this case, it's positive, so we're going to move away from the assumed position at an angle of 86.2 degrees, and we're going to go 7.1 miles, and there we will strike a line perpendicular to the zenith line, and that's our line of position. It seems like a lot of work. Now let's go back to our slideshow, and I'll show you how it looks practically. Slideshow, start from current slide. So here we've got a map. I guess I'll put me right about here so you can see stuff. That's our actual GPS coordinates, 7932 west, 2435 north. We're going to do this first one here. The assumed position was 7923.5, 24.6 north. I just want to make sure, previous. Yes, sorry. And we've calculated 7.1 nautical miles away on a zenith of 86.2 degrees. So watch. Here is the assumed position, that's 79. Maybe this is GPS. It is. That's the GPS position. Yes, it is. So here's the GPS location where these crosshairs line up. So I'll just mark it there. Okay. And now here's my assumed position, 79.23. So 79 doesn't quite get to 30. 24 doesn't quite get to 30. 24.26, right. So that's our assumed position. We are going to draw a line measuring 86.2 degrees. So there's the location of the sun. Remember, this is happening at 15:23 Universal Time, but we're over in the Caribbean, so that's a 4-hour difference in June. So it's like 11 o'clock in the morning, if I'm not mistaken. Let me see here, 1,500 hours. Yeah, that should be like 11 o'clock in the morning. So this line, as you see, I'm trying to get my mouse back. There we go. This line, as you see, is positioned at 86.2 degrees, and I'm going to move that line up the map to the assumed position, same angle, and the length of the line away from the sun, remember, away from the sun, 7.1 miles. Now, this is taken using calipers on the latitude scale off the side of the chart. Now, latitude doesn't change no matter where your map is, but longitude towards the North Pole is very skinny because the lines converge, and longitude towards the equator, the same number of degrees is bigger. So we don't use the longitude scale down here for measuring things. We only use the latitude scale. So we go measure 7.1 arc minutes. That's a part of a degree, right? An arc minute. And we recognize that each arc minute is a nautical mile. So we get that measurement and we put it on our map along that line. So this line here from the assumed position at 86.2 degrees is 7.1 nautical miles long, and I strike using a ruler, a perpendicular at that distance, and look, it goes right through our GPS position. We knew we had to be on that line. We are on that line right there where the GPS location is, although if we don't have GPS, we don't know we're there. We just know we're on that line. But look what happens if I go put these values for assumed position 2 and our dead reckoning. If I go back to my Excel spreadsheet and change the assumed position latitude and longitude to this value, 80 and 24.5, 2435 or 2430, that would be, oh, there's the line of position. There's the new assumed position over here. I just pick it at random, okay? 80 degrees, 2430, okay? There's my new assumed position. The values I get back are minus 25.8, meaning go to the sun, and 86.2, the zenith didn't change, so I still use that zenith angle. I use a rolling ruler. Let's see if I can find my rolling ruler. See, a rolling ruler. I place it on the compass rose on the map. I roll that angle up to the assumed position, and there I strike a line in the direction of the sun because of let's see here. Oh, here, because of, it says 2. I was on the wrong line. And there I make a perpendicular, and guess what? As long as the line is of the length 25.8 miles long, that's this length here, turns out when I strike a perpendicular, it's the exact same line I struck last time. And this time if I use my dead reckoning, which is right here, and I plugged the dead reckoning values, 79.15 and 2436.5, into the spreadsheet, it gives me HC minus HO is 15.5 miles away from the sun at an angle of 86.6. When I put that angle, roll it up to there, that distance is 15.5 miles, and I strike a perpendicular line through that tip of the tip of the line there. It's the exact same position. So no matter which assumed position you use, or whether you use your dead reckoning position as the assumed position, it doesn't matter. The perpendicular line that is struck at the end of the intercept distance is the same line. So you only have to really do it once. You just pick one. I'll make a case later, and I'll show you why, that by using the dead reckoning as your assumed position, you save the most information from your dead reckoning, and you get your position corrected perpendicular to the dead reckoning onto the line of position. It's the most likely position for you to be at in actuality, and it's going to be very likely that it's your GPS position. In fact, let's go previous. You'll notice that, now watch, from the dead reckoning, if I use the dead reckoning and I bring it 15.5 miles away from the sun along 86.6 degrees, then the perpendicular to the tip of that line will be the line of position, and my corrected position from the dead reckoning ends up being my GPS position, my actual position. If I use some other assumed position, the best I can hope for is that I'm somewhere on that line and kind of nearby. But this gives me some better data. It gets me closer to truth using the dead reckoning. And later you can cross another line of positioning, perhaps on a star or a moon shot. You can cross another line of positioning and get a fix. We'll talk about more of that in our next course, or rather lesson 3 of this course, where I'll show you maybe some more details on how to build your own spreadsheet. And in fact, really, I think the next one I'm going to skip. You saw how that spreadsheet was done. Normally, when I teach this course, I actually sit down and we design a spreadsheet together. I think I'm going to skip that in the online series. I showed you enough that you should be able to recapitulate my efforts and build your own spreadsheet if you're interested. I think our next lesson online will be to skip to lesson 4. And I'll show you the spherical trigonometry that underlies the magical formulas that are used to discover HC and zenith, because those values are used to find the lines and the angles that we need to put on the map. to find our location. So we'll take a peek under the hood. I'll show you the spherical trigonometry behind the equations, the spherical law of cosines that we use to make this all work. Thanks for listening, and I hope to see you back next time. I'm George Trimble.